let's continue on with our next module. So for this module, we'll need to learn. We'll need to use the array list that we wrote from the previous module. So that's why I haven't moved to a new project. So, all right. Programs have a cost associated with running them. Okay, so let's go ahead and just list out these costs. The costs of running a program are basically three big ones. You have time, the amount of time it takes to run a program, the amount of time it takes. For it to be a valid algorithm, for something to have a valid algorithm, it needs to have a finite amount of runtime. It's not going to run forever. The other costs are space. In other words, the amount of memory it's going to take up for an algorithm. So how much RAM, how much disk space, you can measure it in various different ways, but memory or space complexity is another cost. So time complexity, space complexity. Another cost that's actually fairly important these days is energy. There we go. Distraction-free mode. Energy is another big one. So the energy cost is rather large. That's very important these days because these days, a lot of computing happens on these things. On a smartphone. The computer, by the way, that is more powerful than what was used to, land the Apollo 11. These are extremely powerful, but unlike the computer that I'm recording on, it's plugged into a wall. It's getting energy from somewhere. That's a big advantage. So I don't really have to care too much about energy. But this little thing, yeah. Have to totally care about how much energy gets consumed by this. So that's one thing we can look at. However, energy costs again can be mitigated. If I have to, I can get a bigger battery. If I have to, I can plug it into a wall. Same thing with space. You can mitigate space in some form. You're running out of space, go out and buy more. RAM is cheap these days. It's insane. Compared to maybe 30 years ago, right? I remember the first time that I had a computer that my father got me when I was in middle school. Well, not me, but it was for the family. But it was I remember that gigabyte of hard disk space being quite a lot of space. Now that's like one good video file, and I've got, 7 terabytes, I think, of just hard disk space on this computer, not counting the solid disks, the SSDs. So, and I bought the 4 terabytes for about $70. When this video is recorded, it's 2019. So, space is not much of an issue these days. But my algorithm takes too long. I'm just going to rush out to the time store and get me some more seconds, right? So, time is the most important resource. None of us, to get a bit depressing on you, none of us know how much time we have left in the world. You have entered this world with your return ticket already punched. So, and if you've got a really important program, well, best you still be around by the time it finishes executing, right? That program is useless if it takes enough time that the sun dies. That program is useless, right? Yes, it's technically a program because there was a finite amount of time, but the amount of time has to be useful. Time is important. Time is the most important, most valuable resource because you cannot buy more of it. You cannot get more time. And thus, when we analyze algorithms to see how these things can run, when we try to compare them, we compare them by the amount of time they take. Also importantly, we don't compare algorithms based on the literal runtime that it's going to take. We don't really care because, some newfangled computer is going to come out and that's going to be able to run stuff faster. But the order of magnitude that a program takes, as you'll see, that's what we really care about, because that's the relationship that determines, okay, yeah, your computer can do it twice as fast, but it doesn't really make a dent in this problem, or maybe it will. So time we really care about. Now, we typically talk about, be it time, space, or energy, we typically use big O notation to denote that. That means the time is going to be no worse than this function. So it simply says that basically the amount of time that this algorithm will take, which is called T of n. T of n is going to be no worse than O of n. It's going to be no worse than O of n. Right? O of n is his worst case scenario. And what O of n sets up is that this algorithm, we say if it has an O of n time, then it is going to have a linear relationship. This is big O notation. Can also be O squared. Can also be constant time. Those are, there's a lot more, but we're going to be learning about those three. We're going to be learning about constant time, relationships, constant time relationships, and that means that basically no matter how big of a problem size we're solving, no matter how big the thing we're dealing with is, it's always going to take the same amount of time to run. A linear time relationship, or O of n, this constant time being O of 1. Linear time, O of n, meaning, and a linear time means there's a linear relationship between the amount of time, amount of items you have and the amount of time it takes to solve something. So if it takes you, say, 100 seconds to solve 100 problems, then doubling that will take the amount of problems you have to 200 means it will take 200 seconds. Multiplying by 10 from 100 to 1,000 means that it will take 10 times as long, right? There's a clear linear relationship between those. And then finally, you've got a quadratic relationship, where that's O of n squared. And that means that basically that when we add one more item, I add a whole lot more work to do. That means when I double the amount of items I have to work with, it's going to take 4 times as long. Or when I have 10 times as many items, it's going to take 100 times as long. For linear and quadratic, the way I like to compare it is linear time. If you've ever had to grade papers, being a TA or something, or grade homeworks, it's something I have to do. But if I've got 50 students, right, then it takes me a certain amount of time to grade all those exams. Okay? And if I had twice as many students, say it takes me 3 hours to do 50 students. If I had twice as many students, it's going to take me 6 hours, ostensibly, right? Some variation may apply, but it's going to take me, 6 hours. Okay. But, and that's a linear relationship, right? If I double the number of students, it's going to double the amount of time I have. And we're assuming that basically I don't get any faster or slower as I grade, On the other hand, I'm grading these exams. Now suppose that I'm super paranoid about plagiarism in my exams. And as a result, what I do is that I check everybody's answers against everybody else's answers, right? So I'm super paranoid about that. Okay. Now imagine I've went from 50 students to 51 students. Okay. Now I have a new student whose exam basically that maybe the TA forgot to give to me, right? I've already done my 50 students, graded them. Now with that 51st student, I still have to compare his answer to everybody else's answer, right? So I have to compare that 51st to all the other 50. And suppose there's a 52nd, then I'd have to compare that guy to the 51 other guys. That's a quadratic relationship. And you can kind of get a glimpse of how much work that would be. So that is the metaphor we'll use, or that is a metaphor I will use. But for right now, we're going to go more for maybe a less theoretical thing and take a look at how to time things.